Okay, picture this, an environment that's got scorching heat, violent nonstop vibrations, and these massive electrical spikes that would just instantly fry your laptop. Well, that's just another Tuesday on the factory floor. So it begs the question, right? How on earth does the sensitive digital brain behind all our modern automation survive that, let alone run perfectly for years and years? So let's really get into it. To even understand the solution, you first have to understand the problem. You gotta appreciate the enemy. And what we're talking about here is an environment that is, and I'm not exaggerating, actively hostile to the delicate little microchips that basically run our entire world. And here they are, the usual suspects, the everyday villains of the industrial world. You've got electrical noise from giant motors starting up, you've got crazy high voltage spikes, intense heat, moisture everywhere, and just constant bone-rattling shaking. Any single one of these would be a death sentence for the phone in your pocket or the computer you're watching this on. And you know, the stakes here could not be higher. A failure isn't just some small inconvenience. It can literally shut down an entire production line, costing a company millions of dollars. But more importantly, way more importantly, it can put people's lives at risk. This is exactly why a special kind of hero had to be created. See, before our modern solution came along, automation was run by these gigantic, tangled messes of wires and physical relays. I mean, just a rat's nest. If you wanted to change one tiny part of the process, forget about it. That meant hours, maybe even days, of painstakingly rewiring the whole thing by hand. And trying to find a problem? Well, that was an absolute nightmare. And out of that chaos, the Programmable Logic Controller, or PLC for short, was born. But listen, don't just think of it as a computer. That's not the whole story. You need to think of it as a computer that's been built from the ground up for a war zone. It's been ruggedized, specifically designed to take all the punishment a factory can dish out and just keep on going. And this shifts, wow, it was absolutely revolutionary. I mean, you went from spending days hunched over, physically yanking and rerouting wires to just typing a few lines of code. The entire control system moved out of the physical world and into software, and that made everything smaller, more flexible, and just so much more powerful. This image right here perfectly shows the PLC's key survival strategy, isolation. You see, the delicate part, the brain, that's the CPU, it's kept completely separate from the tough-as-nails I/O modules. Those are the guys on the front lines, the ones that actually connect to the harsh world of the factory. But that raises a question, right? How do you stop the danger from crossing that bridge? So how does a PLC physically build this invisible force field to protect its most sensitive parts? Well, it all starts with a principle that is so simple, it's actually genius. That's right, an actual, literal, physical gap. It's like digging a moat. It prevents all that dangerous electrical energy from ever having a path to the core components. But wait a minute, if there's a gap, how does the signal get across? Well, the answer is brilliant. It uses light. This amazing little trick is pulled off by a component called an optoisolator, or sometimes an optocoupler. Its entire reason for existing is to act as a one-way bait. It lets the information pass through, no problem, but it physically blocks any electrical threats. It is, without a doubt, the single most important piece of hardware in the entire PLC. So here's how it works. An electrical signal comes in from, say, a sensor out on the factory floor. That signal just makes a tiny little LED flash on one side of the gap. On the other side of the gap, a light sensor sees that flash of light, and it creates a brand new, perfectly clean electrical signal inside the PLC. So what happens if a massive voltage spike comes in from the outside? Well, it hits that LED and just dies. It can't jump the gap. The message gets through, but the danger stays locked outside. Genius. But of course, it doesn't just stop there. That's just the first line of defense. PLCs use a whole suite of protections. They have proper grounding and shielded cables to filter out all that electrical noise, special circuits to handle power surges, and of course a physical design that's just built like a tank. It's what we call defense in depth. Okay, so having an armored body is only half the story. The real smarts, the real intelligence is in how the PLC is programmed to think defensively, to actually anticipate and prevent problems before they can ever happen. And that all starts with the code itself. PLCs are often programmed using something called ladder logic, which is designed to look just like an old-school electrical wiring diagram. What this language does is create really strict, unbendable rules for the machinery, making it physically impossible for a machine to enter an unsafe or self-destructive state. Think of these as the software guardians. You've got interlocks that prevent conflicting commands, like telling a motor to go forward and reverse at the exact same time. You've got fail-safes that make sure if any part breaks, the whole system shuts down gracefully instead of, causing a catastrophe. And then timers and counters make sure every single step in a process happens exactly when it should, in the right order. It's like a digital safety net woven right into the DNA of the machine. So that brings us to the modern factory, right? Where everything is connected. We're in the age of Industry 4.0. Now, this whole philosophy of protection has to go beyond just one single PLC. It has to extend to the entire network of machines all talking to each other. And that is where modern protocols like ProfiSafe come into play. The best way to think of it is as a secure, armored language that all the machines on the network agree to speak. It lets critical safety commands, like a big red emergency stop button, travel on the exact same wires as all the normal data, which means safety isn't an afterthought, it's baked into the very fabric of the system. And this really is the ultimate evolution of that original PLC philosophy. We've gone from just protecting one little box to creating entire networked fortresses. In these systems, safety and reliability are designed in from the ground up, even protecting the communication itself from being hacked or manipulated. So here's the big takeaway. The core principles that were pioneered by the PLC, that physical isolation with things like opto-isolators and that guardian logic with software interlocks, they're not just for factories anymore. As automation finds its way into our homes, our cars, and pretty much every part of our lives, the lessons learned from this indestructible little brain are more critical than ever before. So it leaves us with a pretty important question. How are we going to build a safe, automated future for everyone?
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.